Hello everyone. In this video, a DC to DC buck boost converter is tested. A buck boost converter is a step down and step up converter. The output voltage of the buck boost converter can be lesser or greater than the input voltage. The converter can operate in two modes. During mode 1, the switch is in the on condition, and during mode 2, the switch will be in the off condition. The circuit of the buck boost converter is shown here, which consists of a switch, an inductor L, a diode D, capacitor C, and the load. The switch can be operated with a duty ratio of K is equal to T by T on. The polarity of the output voltage will be negative to that of the input voltage polarity. Hence, this converter is also called as inverting regulator. The various applications of buck boost converter includes battery power system, power amplifier, automotive, adaptive control, DC motor drive, and self-regulating power supply. During mode 1, the switch is in the on condition, the diode is in the open condition. During this mode, the inductor stores energy in it. At the same time, the capacitor energy is dissipated through the load. In mode 2, the diode is in the on condition and the switch is turned off. The inductor with stored energy during the mode 1 is dissipating through C and load. During this mode, the C is charged. The various waveforms of the mode 1 and mode 2 are depicted here. The first waveform is the PWM signal. The second waveform is the inductor current. The inductor current rises from minimum value to a maximum value Imax during mode 1, and in mode 2 it falls from Imax to Imin. Third waveform is the source current waveform. Fourth waveform is the diode current waveform, and the fifth waveform is the capacitor current waveform. The capacitor current is equal to minus I0 during mode 1 and is equal to IL minus I0 during mode 2. And the last waveform is the capacitor voltage waveform. In mode 1, we can write VL is equal to L into dIL by dt, that is equal to Vs, which can be rewritten as L into del I by T on equal to Vs, where del I is nothing but I max minus I min and dt is T on. And we can write the same equation as L into del I by Kt equal to Vs, as T on can be written in terms of the duty ratio as K into T. And hence we can write del I is equal to Vs Kt by L, and also we can write Kt equal to del I L by Vs. Similarly, for mode 2, we can write the inductor voltage L into dIL by dt equal to V0, and dIL can be substituted as minus del I, as the current it falls from I max to I min, and dt can be written as T off. And again, we can substitute T off is equal to 1 minus K into T. Therefore, L into del I by 1 minus K into T is equal to minus V0. Hence, we can write del I is equal to minus V0 into 1 minus K into T divided by L. Also, we can write 1 minus K into T equal to minus del I L by V0. To obtain the expression for output voltage, we have to equate equations 1 and 2. So, Vskt by L is equated to minus V0 into 1 minus K into T by L. Rearranging the above equation and simplifying, the output voltage expression is derived as V0 equal to minus Vsk by 1 minus K. So from this expression, we can say that the output voltage can be lesser than the input voltage for K lesser than 0.5, and if K is made greater than 0.5, your V0 can be more than Vs. In order to obtain the ripple current expression, we have to take T is equal to T on plus T off, which can be substituted as Kt plus 1 minus K into T. Substituting for Kt and 1 minus K into T from the expressions 1a and 2a, the value of T can be written as del I L by Vs minus del I L by V0. Rearranging the terms, we can write del I is equal to T Vs V0 by L into V0 minus Vs, and substituting T is equal to 1 by F, L I is equal to Vs V0 by F L V0 minus Vs. From this expression, L can be written as Vs V0 by F del I into V0 minus Vs. And the ripple voltage expression is del V is equal to Vc minus Vc of 0. Vc can be written as 1 by C integral IC dt plus Vc of 0. So finally we will get del V is equal to 1 by C integration from 0 to t on IC dt, and IC during the on period is nothing but the magnitude of IC is nothing but the output current. So substituting IC is equal to I naught and integrating over 0 to t on, the del V expression is I naught t on by C, which can be written as I naught kt by C, and hence del V can be written as I naught by k. Del V can be written as I naught k by fc. Again, C can be written as I naught k by f into del V. So we have derived the ripple current and ripple voltage expressions, and we have also derived the expressions for L and C. Now the condition for continuous conduction mode need to be obtained. The continuous conduction mode will take place when the ripple current is 2 times the load. The condition for continuous conduction mode can be obtained by substituting the ripple current expression as 2 times the load current and the ripple voltage expression equal to 2 times the load voltage. So the derivation of the critical values of L and C can be obtained by equating del I equal to 2I naught, and substituting for del I and rearranging, we will get the LCR value as VSR by 2F into V naught minus Vs. Similarly, del V is substituted as 2V naught for deriving CCR. Substituting for del V, the expression for CCR is equal to K by 2R into F, where R is the load resistance. Thank you.